Okay, sorry about that. I'm back. So I want you to again look over here at this atomic absorption spectra. So you can see that's exactly opposite. I'm going to flip back, maybe. So here you can see these lines on hydrogen. And then if you look at the absorption spectra, you see it's just the opposite. And then here we have helium and neon. So this is just the exact opposite. So here we have white light, which has all the colors of the rainbow. Then your sample. So that's going to be either your hydrogen gas, helium gas, neon gas, whatever it is. So what's going to happen is it's going to absorb out those frequencies where it does, and then it's going to go through and give you this kind of spectra. So the reason it's doing that is it's getting those very particular frequencies that it needs, and that's exciting it. It's basically absorbing it, and the electrons are being promoted to a higher energy level, which we're going to talk about some more. And then that's how you get this absorption spectra. So emission and absorption spectra are just opposite of each other. All right, so quantized energy. Radiant energy is quantized. So that means it has values restricted to a whole number multiples of a specific base value. And we'll talk a little bit more about what that means. The quantum is the smallest discrete quantity of a particular form of energy, and a photon is a quantum of electromagnetic radiation or a particle of light. So it's something that's really difficult to understand. But quantized energy states are discrete energy levels. Hold on one second, I'll be right back. Okay. Sorry, this working from home thing is nonsense. Okay, so quantized energy. You have these quantized states are discrete energy levels. So you can think of those as steps. So if you're going up a stair, your foot is here, and then your foot is here, and then your foot is here, and then your foot is here. But your foot is never between here and here, right? There's nothing to stand on. An unquantized state, which is more what we're used to, our physical world appears to us to be unquantized. So that would be like a ramp. If you're going up this ramp, it is unquantized. So that's kind of how electrons are. So they can be here and then here, but they can't be anywhere in between, which I think is really freaky. It's like a solid thing. So it's like, imagine if I were in class. If we were in class, I would say if I were walking across the classroom, you can see me at every point in space. But imagine if I were walking across the classroom and I just suddenly disappeared and appeared 5 feet in front of me, and then another 2 feet in front of me. That's kind of how electrons move. That's how I like to think of it. So it's quantized. They can't step between the steps, but they can only step at certain steps. And that's where those absorption and emission spectra come from. Those are the different steps that electrons are allowed to make. So hopefully your mind is blown right now. Okay, so then we have what's called wave-particle duality. Light has properties of both a wave and a particle. Wave-like behavior of radiant energy. So we have wavelength and frequency to describe it. And then we have particle-like behavior of radiant energy. So like that photoelectric effect where we were shining light on the metal to eject the electrons, that's more of particle-like behavior because you're using the light to physically eject a physical object, right? And the particle-like behavior, we have quantized packets of energy. All right, so the next calculations I want you to be able to do are these calculating the energy of the photon. So remember, a photon is just a little packet of energy, of light energy. So it's like a light particle. So this dude named Planck proposed that the energy of the photon was directly proportional to the frequency of the wave of its corresponding radiation. So energy equals h nu, where nu is the frequency and this is Planck's constant. So this is the thing that's making it quantized. this constant here. So then if you recall that C equals lambda times nu, then we can put in for nu hc over lambda. So now we have two equations, it's basically the same equation, for the energy of a photon, which is either Planck's constant times the frequency or Planck's constant times the speed of light divided by the wavelength. So if I'm asking you to calculate the energy from a frequency, you would use this, and if I'm asking you to calculate the energy from a wavelength, you would use this equation. So H is this number here, 6.626 times 10 to the negative 34 joule seconds. Einstein's discovery of the photoelectric effect supported Planck's model. So the discovery here, the energy of a photon is quantized. So that just means like the steps in the ramp, the energy of the photon can only come in discrete packets, like the steps. Okay, so maybe pause it here and calculate the energy of a photon of red light at 685 nanometers. So just take that equation from the previous page. It's also on your handout, and you should be able to figure this out. So pause it if you need to. I'm going to keep going. All right, so here we have the wavelength, 685 nanometers, Planck's constant, and the speed of light, and we want to know the energy. So again, we're going to need to convert 685 nanometers into meters, and then we're going to use this equation here. All right, so here we converted to meters, and then we're going to put in Planck's constant, which is always this number with units of joules times seconds, speed of light in meters per second, and then the wavelength in meters. So again, just like always, make sure that your units are canceling. So the meters are canceling here, the seconds here are canceling, and then we're left with joules, which is our unit of energy. So that's a pretty small number in terms of joules. So remember for water, you know, it had that specific heat of, it takes 4.184 joules to heat up 1 gram of water, 1 degree Celsius. So 2.9 times 10 to the minus 19 is pretty, you're not going to be able to heat up any water with that, right? But it's just 1 photon of red light. So 1 photon of red light you wouldn't even be able to see with your eye. So it should have a small amount of energy. All right, so make sure you know how to do those types of calculations. Now we're going to look at the Bohr model of the atom. So Niels Bohr came up with this model, and it still works pretty well for hydrogen only. So the Bohr model of the atom is we have the nucleus where our protons and our neutrons are, and then we have, remember it's a hydrogen atom, so how many electrons are there? Just 1. But that electron could be in different locations. So if it's in the ground state, it's right here in n equals 1. I'm sorry if you can hear other stuff going on in my house. So it's going to be at n equals 1, that electron. Then if it absorbs the proper amount of energy, it could be promoted to n equals 2 or n equals 3. But if it doesn't have the exact right amount of energy, then it's not going to happen. Okay? So those are our different energy levels. So distance from the nucleus is higher energy. So the farther the electron gets from the nucleus, the higher energy it is. And if you add enough energy, you can actually eject it from the atom entirely. And that's how we get those ions that we talked about, you know, first week. Okay, so here's how it happens. When hydrogen atom absorbs energy, an electron, so it's absorbing, this light's coming in, and then it's giving energy to this electron, so it's going to go farther and start orbiting in a different place. So it's excited to a higher energy orbit. The electron then relaxes back to a lower energy orbit, emitting a photon of light. So it's not really going to stay at this high energy thing. It's not, it's just not. So it'll relax back, and then it'll emit a photon with the energy that corresponds to that exact distance there. So we have energy absorption and emission. So that's just like our absorption and emission spectra that we looked at before. So this is what the electrons are doing to produce those spectra. So recall the hydrogen emission lines, and this is what those colors, those lines, correspond to. So here's our nucleus, and our electron can either be in n equals 1, 2, 3, like that. So if the electron relaxes from n equals 3 to n equals 2, it'll emit light, because remember we have that conservation of energy. So if the electron's going to relax, then that energy has to go somewhere. So it's going to release red light right there. If it goes from n equals 4 to n equals 2, you're going to get this blue-green light, because only that exact amount of energy can happen, right? It can't relax to here, because that would be halfway between the steps. If it relaxes from n equals 5 to n equals 2, then you get this violet light. So as you can see, there are lots of other possible transitions in there, but they're not all in the visible region. So when we're looking at these absorption and emission spectra, we're just looking at visible light. Okay, so the Bohr model of hydrogen atoms. So we can actually calculate the energy between of these different transitions between different orbits. So electrons in hydrogen atoms occupy discrete energy levels and exist only in the available energy levels. They may move between energy levels by either absorbing or emitting energy. They have energy levels designated by specific value for n. And the difference between energy levels, delta E here, is given by this equation. So this is just a constant number here. A lot of times given by, I think, capital R subscript H, is negative 2.178 times 10 to the minus 18 joules, big parentheses, and then 1 over n final squared, so that's the n that you're ending up in, minus 1 over n initial squared. So those n's correspond to these. So say it went from 4 to 2, then 4 would be your n initial, and 2 would be your n final. Okay, so this is also an equation that I want you to know how to work with and use. All right, these are our electronic states. So energy level is an allowed state that an electron can occupy in an atom. Ground state is the lowest energy level available to an electron in an atom. An excited state is any energy state above the ground state. And the electron transition is a movement of an electron between energy levels. So this just shows you some different series of transitions. So n equals 1 is the orbit that's closest to the nucleus. And then we go to n equals 2, 3, 4, 5, 6, and infinity is when you would eject it from the atom completely. So one thing I do want you to note is that the energy between 1 and 2 is quite high, and then 2 to 3 a little smaller, and they get closer and closer together. So I want you to know that they get closer together in energy as they go higher up. So remember that corresponds to distance from the nucleus as well. So those energy levels get closer and closer. But keep in mind that the transition from n equals 1 to n equals 2 is higher than any other single transition there is. All right, so if we're going this way, that's the absorption of energy, and here we're emitting energy. So this one is called the Lyman series, and these are all ultraviolet, so we wouldn't be able to see those ones. These are the ones, the Balmer series, these are the ones that we saw in that emission spectra, and these are the ones in the visible region, so the colored light that we can see. Then you have a Paschen series, which is in the infrared region of the electromagnetic spectrum. Okay, so let's practice using this equation. And I believe if you have your handout out, this should be one of the examples on your handout. So here's the equation we're going to use. What is the energy change when an electron drops from the 5th energy level down to the 2nd energy level? So go ahead and pause it and work it out, and then push play when you're ready. All right, so n final in this case equals 2, and n initial equals 5, and then we just plug that into this equation here. So n final goes here, so 5 squared is 25, n initial here, oh shoot, sorry, backtrack, N final was 2, so 2 squared would be 4, and then N initial 5, so 5 squared, 5 times 5 would be 25 right here. So here you plugged it in, 2 and the 5, and make sure you get them in the right place. And then you work it out, and here's your energy change. So the energy change when an electron drops from the 5th energy level down to the 2nd energy level. And I want you to think for a second, why is it negative? So think back to that thermochemistry, right? If it's negative, it's releasing energy. So the electron is dropping from higher energy state to a lower energy state. So that's going to correspond to a negative energy. So similar concept that we worked with in chapter 5. Okay. A small amount of energy, but it's the energy change for just a single atom. And the sign of delta E is negative because the energy is being released. All right, so that Bohr model has a lot of limitations. So first, its strengths. It accurately predicts energy needed to remove an electron from an atom, which is known as ionization, and we're going to get to that at the end of chapter 7. It also allowed scientists to begin using quantum theory to explain matter at the atomic level. Some of the limitations: it does not account for spectra of multi-electron atoms, which is every single atom other than hydrogen. So that's a lot. Movement of electrons in atoms is less clearly defined than Bohr allowed. So it actually turns out where the electrons really are is incredibly confusing. So they're not just orbiting like little planets, like those drawings, which is unfortunate because that's like a lot easier for our brains to comprehend. So the electrons are actually kind of doing a lot of other things. So where the heck are the electrons and how do we describe their paths? I think I'm going to stop there for this recording because next time we're going to get into talking about orbitals and all the different numbers associated with them. So I'm going to make that into a different video. So thanks for hanging in with me. If you're still there, I appreciate it. And I'll make another video for the next part.